A key development that has captured the attention of the automotive industry is the introduction of Tesla's next-generation 4680 battery. This battery will power the Tesla Model Y Juniper, slated for a 2025 release, and it brings numerous innovations. Recent revelations about significant chemical changes from the first generation of these cells underscore their evolution, as currently utilized in the Model Y. Understanding these improvements requires examining the reasons behind Tesla's modifications to the 4680 battery. The first generation batteries had shortcomings in charging performance and energy density. Tesla also faced challenges with the dry electrode coating DB process for cathode production, which, despite reducing manufacturing time and costs, presented technical difficulties. These issues were compounded by the departure of the dry electrode coating's inventor last year. However, there have been promising updates. Lars Moravy, Tesla's vice president of vehicle engineering, mentioned during the Q1 earnings call that 4680 battery production is ahead of Cybertruck production, with enough capacity to support over 1,000 Cybertrucks per week. Yet, without addressing the main performance issues of the 4680 battery, mass production could still yield a subpar product. At a previous investor conference, Drew Baglino, a Tesla executive, announced an improved version of the 4680 cells with a 10% increase in energy density compared to the first generation, achieved through process optimization and mechanical design. In Texas, Tesla is gearing up to launch the Cybertruck with these enhanced cells, boasting 10% higher energy density. Significant changes, particularly in the battery's chemistry, mark the improvements in the second generation of the 4680 battery. A major advancement was the increase in energy density, primarily achieved by a lower-profile battery cap design, which creates more space for electrodes. The potential for a thinner external cell was also considered. James Murdoch and his team have detailed the changes in the cathode and anode chemistry of the 4680 Gen 2 battery. According to Murdoch, the new Model Y battery, produced at the Austin Gigafactory in Texas, uses NCMA chemistry with 82% nickel, 11% cobalt, 5% manganese, and 3% aluminum. Compared to Gen 1, the nickel and aluminum content increased slightly, while cobalt decreased. The anode is made of natural graphite with a small amount of silicon, similar to the Gen 1 anode. These adjustments are critical to understanding how Gen 2 outperforms Gen 1 of the 4680 battery. The first generation 4680 battery cells featured an NMC 8811 cathode chemistry, comprising 80% nickel, 10% manganese, and 10% cobalt, with a gravimetric energy density of 232.103. The Cybertruck cell initially lacks silicon in the anode, but adding even small amounts of silicon can enhance battery performance by increasing energy density and efficiency. Tesla aims to meet its energy density targets for the Cybertruck cell by incorporating NCMA chemistry. Additionally, Tesla is working on integrating NMC 955 cathode chemistry to replace NMC 811 chemistry and experimenting with asymmetric lamination to increase the capacity of the battery jelly roll that fits into the 4680 can. Tesla is also testing NMC 973 chemistry, which is anticipated to debut in late 2024. These changes are expected to significantly improve the performance of the Model Y and other future Tesla vehicles. Altering the battery chemistry, such as increasing aluminum and reducing cobalt, is a smart move since cobalt, despite improving battery life and safety, is expensive and raises ethical concerns. The new chemistry can lower battery costs and consequently reduce car prices. NCMA cathodes, incorporating manganese and aluminum, reduce cobalt dependence and address cost and sustainability concerns without significantly compromising battery performance. Including aluminum also enhances the cathode's structural stability, increasing the battery's safety and lifespan. Tesla will likely continue using NCMA cathodes, given their effectiveness in reducing cobalt dependence. It is believed that LG Chem is supplying finished cathode rolls or cathode powders to Tesla, as LG Chem pioneered NCMA chemistry. LG Chem recently started building the largest cathode factory in North America, in Clarksville, Tennessee, with a $1.6 billion plant offering an annual production capacity of 60,000 tons, enough to power approximately 600,000 electric vehicles per year, each with over 300 miles of range. Additionally, Tesla is said to have secured a substantial electrode deal with LG Energy Solution, a subsidiary of LG Chemistry. According to the Korea Economic Daily, an industry insider stated that Tesla's purchasing team recently ordered electrodes worth 6 trillion won from LG, with a contract expected to be signed in the second half of the year. The supply will begin next year and is expected to last 6 to 7 years, coinciding with Tesla's facelift launch cycle and aligning with the release of the Model Y Juniper. The ordered electrodes are estimated to equip 1.3 to 1.4 million electric vehicles, representing about 70% of Tesla's total production last year. Battery manufacturers typically combine anode and cathode materials with conductive substances and binders to produce electrodes, which are then assembled into battery cells and supplied to automakers. Tesla's recent electrode order indicates they are acquiring these components just before the assembly stage. Although the specifics of the electrodes, cathodes, anodes, or both, were not disclosed, it is believed that Tesla is primarily buying cathodes, as it seems they have figured out how to make anodes entirely with the dry process. Cathodes have posed a greater challenge. Starting this August, LG Energy Solution will assist Tesla in ramping up 4680 battery production, with mass production beginning at their Korean plant between August and September, according to CEO Kim Dong-myung. LG is exploring options to produce cylindrical batteries in the 4680 format at its Nanjing, China, facilities. Additionally, LG Energy Solution plans to start producing lithium iron phosphate (LFP) batteries, primarily sourced from Chinese manufacturers, in the second half of 2025. LG is also in supply discussions with other automakers, such as BMW, GM, and Stellantis, who are increasingly adopting the cylindrical 4680 format due to its advantageous properties. A report from the Chinese outlet Latepost detailed Tesla's ambitious goal to reduce the cost of its 4,680 batteries below the purchase cost of batteries from suppliers. The report suggested that if this cost reduction goal is not met by the end of the year, Tesla might consider abandoning the 4,680 project. Several 4680 battery engineers expressed confidence in achieving this goal, believing that if Tesla avoids insisting on manufacturing cathodes with the dry process and focuses on improving production capacity, yield, and cost solutions, the 4680 battery project will likely meet its cost reduction targets. In summary, Tesla's development and refinement of the 4,680 battery cells signify a major leap forward in battery technology, addressing previous challenges in performance and production. By integrating advanced chemistries like NCMA and exploring innovations such as asymmetric lamination and the incorporation of silicon in anodes, Tesla aims to significantly enhance energy density and efficiency. These improvements are expected to bolster the performance of upcoming models like the Model Y Juniper and the Cybertruck, while also potentially reducing costs and increasing sustainability. Collaborations with suppliers like LG Chem and LG Energy Solution are crucial in scaling production and meeting these ambitious targets. If Tesla successfully navigates the remaining technical and cost challenges, the 4,680 battery project could set a new standard in the electric vehicle industry, driving innovation and affordability in future Tesla vehicles.